Good day, Math 30-1s. Today we are continuing in our polynomials unit, and we are finishing things off in the 3.4 lesson talking about graphs of polynomial functions. Last day we were essentially looking at more synthetic division. We were looking at an extension of the remainder theorem into the factor theorem, hoping essentially for factors that are perfect, no remainder needed. So the point of today is to determine the relationship between zeros, roots, and x-intercepts, sketching a graph without technology, and at the end modeling a problem that is a polynomial. So the first new word today is talking about something called multiplicity. And multiplicity is talking a little bit about behavior at an x-intercept. It is essentially the number of times that a function has an x-intercept, and that's what determines its behavior there. So we'll kind of investigate three possible scenarios, and the only three possible scenarios. If I were to say, what does x minus 3 look like? The hope is that we could see a slope of 1 and a y-intercept that is negative 3. Or you could think about a line that is shifted 3 to the right. Think about it as a binomial. It's y equals x, shifting 3 to the right. But it would still also have a y-intercept that's negative 3. But I'm going to think about it a little bit as a shifting 3 to the right for a moment. It is linear, x to the 1. If we have an x minus 3, again, same binomial, but this time it has a squared on it, we know that this is a quadratic, shifting 3 to the right. So I'm going to again say this has an x-intercept of 3, but this time I'm going to say that it looks like a parabola. It just touches the x-axis. And lastly, x minus 3 with a cube on it again has an x-intercept of 3, but it has a different behavior. Its multiplicity is 3. Its behavior is a little bit different. This is called an inflection point, and what it does is it looks kind of like it wants to be a parabola on the bottom side, but then it changes its mind and it finishes the parabola on the other side. That's probably the easiest way to approximate an inflection point. Give it a try. So the word multiplicity is again talking about the power on the binomial, the number of x-intercepts that it has. So this is 1x minus 3. This is 2 x-intercepts at the same location. This is 3 x-intercepts at the same location. So the number of times that a function has that x-intercept determines its behavior there. And there are only 3 cases. If there's a multiplicity of 1, it passes through as a line. If your multiplicity is even, 2, 4, 6, and so on, it touches like a parabola. It does not pass through, it touches like a parabola. And if the multiplicity is odd, it passes through as an inflection point. Now this is the case for 3, 5, 7, 9, and so on. And these are the only 3 possible cases. That's it. So let's examine what this might look like when we're given a factored form, something like an x times an x plus 2 times an x plus 2 times an x minus 1, x minus 1, x minus 1, written with a multiplicity of 1, multiplicity of 2, and a multiplicity of 3. Now if I were to ask you to sketch this without a calculator, this would seem potentially overwhelming. But let's start with the end behavior. There is some things we can start with. The degree of this function is a power of 3 and 2 and 1. If these were all added up together, we would have an x to the 6, which makes this an even degree function. Remember, the degree of a function is the highest power in simplified form. So if this was all multiplied together, there would be an x to the 6. The leading coefficient is created from the number in front of the term with the highest power. So if this was all put together, there would be an x cubed multiplying by an x squared times an x. There is a number 1 in front of that. So I'm going to say that the leading coefficient is a positive. We also know that the x-intercepts occur in very specific places. So we know they occur at x equals 0, at x equals negative 2, and at x equals positive 1. And I could have stretched this out a little bit because I have lots of room, but that's okay. So we do know that the end behavior for an even positive function should start in the top left and end in the top right. We have 3 x-intercepts and something different happens at each. So let's examine what happens at -2. It has a multiplicity of 2, an even multiplicity. So this should pass to our -2 and touch like a parabola. And then at some point it's going to go through 0, and that x equals 0 has a 1 on it. That means it passes through as a line. So I don't know how high this goes at this point, but I know that it has to come back around and pass through as a line. And then for the x equals 1, or x minus 1 binomial, it has a cube on it, and this is going to pass through as an inflection point. So I'm going to start a parabola on the bottom and finish it on the other side, and in fact, there's no more x-intercepts. It continues in the upward right direction as it's supposed to, which confirms our initial assumptions. If you wanted to check on your calculator, type that in. You might have to change your y value windows and just see if this matches up. The y-intercept is always a helpful addition to see where this kind of goes, but in this case it was right at the origin. So there is 2 more to try, and if you wanted to pause the video, you're more than welcome to. Otherwise, I will continue with both of these. So what we're doing again is determine the end behavior, and I see a power of 2, 3, 4. 4th degree makes this an even. I know that there's an x squared times an x times an x times a negative, which makes this ultimately a negative even function, opening quadrant 3 to quadrant 4, bottom left to bottom right. I know this goes through a positive 4, it goes through a positive 1, and it goes through a negative 1. So a good estimation, and then we can start to say what happens at the x equals -1. Pass through as a line. So pass through as a line. At the 1, it has a multiplicity of 2, so this should touch as a parabola. And then at the 4, it should pass through as a line. And in fact, it continues in the trend that it's supposed to, confirming our initial assumptions. And here is a sketch of a 4th degree function, which is a little bit complicated. And the very, very last one, we have a x to the 3 and a 1 and a 1 and a 1. That makes a 3, 4, 5, a 6th degree function with a degree of 1, with a leading coefficient of x cubed, x, positive. So this is again a top left, top right, and this has x-intercepts at 0, -4, a 1, and a 2. So at the -4, it has an inflection point, so we'll come down as an inflection point. The next one's at 0, and that passes through as a line, so this is probably going to dip down quite far, and then it'll go through a line, and again continues in the trend that we are expecting. Now these factors can get as complicated as we want, but this would tend to be a 3, 4, 5, 6, a 6th degree function, which is actually beyond the scope of the course. We are limited to degrees of 5, but it is, again, applicable to any even positive function. So what we learned was how to graph in a factored form. And as I give us a new question which says, try as best you can to graph this without a calculator, many people would look at this and say, I can't. It's not factored. And that brings us to our connection to the unit, which we've just learned last day how to factor a cubic, quartic, or quintic function. So your first step is factor this. How do we factor? Go back to yesterday and talk about factors of the constant term. You need to in fact test x equals a positive -1 or a positive -2. Hopefully one of these work. Let's try and see if one works. And what we end up with is a -1 cubed plus a 3 times a 1 minus a 2. What comes out is a negative 1 plus 3 minus 2. And in fact, we do have a negative 3 and a 3. So the remainder is 0, which means x equals 1 is a root, and that means x minus 1 is a factor we are going to work with. So as we do our synthetic division, we have our original polynomial negative 1x cubed plus 0x squared, careful, plus a 3x minus a 2. We are dividing by x minus 1, and we continue with our synthetic division cycle of multiply, subtract, multiply, subtract, multiply, subtract. The 0 remainder is what we were hoping for because that's what we confirmed before, and we can factor this to say there's an x minus 1, leaving us with a negative x squared minus x minus 2, and no remainder. Now, I don't really like to see that negative in front of an x squared, so I'm going to factor a negative out of the quadratic and just write it out in the very, very front. This gives us a x squared plus an x plus a 2. Nope, this should be a positive 2, so this should be a negative. That is actually kind of important because it wouldn't have factored otherwise. So if we factor with the grade 10 and 11 approach of much simpler scenario, we have this as our 3 factors. Now you might say each of them have a multiplicity of 1, but some of you have already noticed that there is a pair of binomials that match. So I'm going to write the official polynomial in factored form up here as a negative x plus 2 times an x minus 1 squared. Because there were 2 factors that matched, we actually have a multiplicity of 2, thus connecting our graphing and our factors of synthetic division. So we have a cubic function, negative leading coefficient. I'm looking at the original one, not the factored form. Which says top left to bottom right, quadrant 2 to quadrant 4. This goes through a negative 2 with a multiplicity of 1. It goes through a 1 with a multiplicity of 2, and it should pass through as a line, touch like a parabola, and then continue on to the bottom right. Now if you want it to be a little bit more precise, we could maybe say what the y-intercept is, plug a 0 into the x and get a 0 plus 2 times a 0 minus 1 that is squared, and that makes a negative 1 squared, 1. 1 times a 2, 2. 2 that is negative, and that is your y-intercept. And so there's a little bit more accuracy we can gauge. Now, this is not perfect because we don't know what the minimum is. We don't have a scale on here, but this is a much more impressive feat than we had done yesterday and in previous grades. So that is the biggest scale kind of coming out of today. Trying to work backwards is also an impressive scale, and if I were to give you a graph, could you reproduce the equation or a possible equation? Because remember, if I were to give you an x plus 1 factor that touches with a multiplicity of 2, it technically could have a multiplicity of 4 or 6 or 8 and so on. So we're asking for a possible equation. So the first thing we might do is talk about the end behavior, and this goes from the bottom left to the top right, so maybe it's a positive leading coefficient. And then let's write down all of our factors, our x plus 4, our x plus 1, our x minus 2, and our x minus 5, and they each have their own multiplicity. The x plus 4 looks like it passes through as a line, so there's a 1, which you don't have to write. The x plus 1 factor touches like a parabola, we'll call it a 2, but it could be again a 4, 6, 8, and so on. 2 passes through as a line, and 5 looks like an inflection point, so we'll call it a 3, but it could have been again a 5, 7, 9, and so on. Often a good question asked is, what is the minimum degree of this function? I can look at these and say 1 and 3, 1 and 2 and 1 and 3 adds up to a 5, 6, 7. So the minimum degree could be a 7. Again, if this was a 4 or a 6 or something higher, and if this was a 5 or a 7 or a 9 and higher, The degree could be much larger, but I picked the smallest possible multiplicities to use, and that makes a minimum possible degree of 7. But this is a possible equation for the graph. If we were provided one more point somewhere on here, we could define an a value and actually number crunch its entire shape with the proper vertical stretch. But we don't know what a value on here is for a, so we'll leave it as it is. For our second last question today, example 3, we're going to think a bit like a diploma. Now, there are many conceptual and problem-solving questions that will be asked with a 70% of the diploma being non-procedural. So, given a graph to the right, it could be created as a product of which of the following graphs? Now, this would be a great numerical response question or some sort of index key to select from. But when you're thinking about what creates this, we're supposed to be thinking about x equals a, x equals 0, and x equals c. Now, we can look at this and say, well, there's probably going to be an x plus a factor, there's probably going to be an x, and there's probably going to be an x minus c that happens more than once, so maybe we'll say that's a squared. So a product of what is going to make this? I also am a little bit worried because I see that this goes from the bottom left to the bottom right, so it has to have a negative x somewhere in there. It has to have a negative leading coefficient. So we're given 4 graphs, and they all have their own x-intercepts. One has a c, one goes through 0, one goes through a, and another goes through a. Which one of these produces an x plus a factor? Which one of these produces an x, and which one of these is x minus c? Now, these graphs all have their own equation, y equals x minus c. That's, again, a linear function, c units to the right. This graph is y equals x. This one is negative x minus a, or negative x plus a. And this graph is y equals x plus a. Okay? It's going through the positive slope. This one was a negative slope. So what's going to create this? Well, if we have an x plus a, we need graph 4. X is 2. And what is x minus c? That is graph 1, and that's going to graph 1 again. So any combination of 4, 2, 1, 1, or if it was ever asked numerically, you'd say 1, 1, 2, 4. But this is a extra challenging question to think about. A polynomial function is technically a composition of multiple functions, multiple factors. Our very last question of the day is an application of polynomial functions, and we've seen volume of boxes as cubic functions before, and so this is what we're going to investigate as of right now. So this last question, example 4, says Mr. Lemko makes an ice sculpture and the block of ice is 3 by 4 by 5, and he wants to reduce the dimensions by the same amount to create a new volume. So here's a block of ice which currently is 3 by 4 by 5, but we're going to reduce the dimensions by maybe 1 or 2 or a half of a foot, some value that we're going to sort of take everything in by the same amount. Ultimately, the volume needs to be 24 cubic feet. How much does he remove from each length is the question. So we have a volume which is a 5 minus an x, a 4 minus an x, and a 3 minus an x. Our hope is for the volume to be 24. Now, when you look at this, you do see factors which might lead you to think you've got x-intercepts of 3, 4, and 5, but that only works if your output is a 0. So we're ultimately looking to solve this equation, what is x? Problem is, there's a 24 in the way. So what we actually have to do, take a deep breath, we have to expand the 3 factors on the right, bring the 24 in with the other constant term, and then factor. And this will take a little bit of work. Feel free to pause the video if you like, but I'll continue. So as we expand the function on the right, we've got 12 minus a 4x minus a 3x plus an x squared. And then we've got a 5 times a 12, 5 times a negative 7x, and a 5 times a x squared. We have a negative 12x, a positive 7x squared, and lastly a negative x cubed. We'll tidy it up a little bit just to make sure that we don't have too many unlike terms. And we've got a negative 35x and a negative 12x makes a negative 47x. We have a 12x squared, and we have a negative x, that is a cubed. We can subtract the 24 over and make this officially a 0, which will be nice. So we have 36 minus 47x plus 12x squared minus an x cubed. Now we can write this in a bit of a different order and maybe make sure that the x cubed is a positive to feel a little bit more comfortable. So we'll change the signs of all those as we reorder this. So x cubed minus a 12x squared minus a 47x plus a minus a 36 plus negative. Question is, factor so that we can get our x-intercepts to solve. So we do have to test, and hopefully x equals 1 works because we have a lot of factors that could work. We have 1, 2, 3, 4, 6, 9, 12, 18, 36, all positives and negatives. So let's plug in a 1 and hope that it works. A 1 cubed minus a 12 times a 1 squared plus a 47 times a 1 minus a 36. We have a 1 minus 12 plus 47 minus 36 gives us an 11, and a negative 11 is in fact a 0. So conveniently the first one worked, and if x equals 1 works, then x minus 1 is a factor. That was a little lucky, we'll say. So we can go into our synthetic division and divide the x cubed minus 12x squared plus 47x minus a 36 by an x minus 1 and complete our cycle. Multiply, subtract, multiply, subtract, multiply, subtract for the 0 remainder. This gives us an x minus 1 times an x squared minus 11x plus a 36. Now, we do have already one solution that x equals 1 is definitely going to work. So we could take 1 off of all those and there is an answer, but maybe there's more. Maybe this factors and gives us another answer, or maybe it's a decimal answer that's a little bit more messy. Now, you might graph this just to see if it actually does produce a solution, or you could use your discriminant to check if you wanted to do this algebraically. But if you graph this in your calculator, you're looking for an x-intercept. If it has one, you get an answer from it, and it might be a decimal. If we do the discriminant and say, what is b squared minus 4ac? If it's negative, we know there's no solution to this, and our only answer would be 1. Let's just check. We have a negative 11 that's squared, minus a 4 times a 1 times a 36, and this gives us 121 minus a 36 times 4. So 36 times a 4 is a 24, and there is 144. Already I see that we have a discriminant that is less than 0, so I'm getting no solution from that, which means the only answer is x equals 1. Question is, how much does Mr. Lemko remove from each length? 1 foot is removed. And that is the final answer. Thus ends our Chapter 3 Polynomials unit. Good luck in your practice.